academic growth of our faculty and researchers. Once again, I extend my heartfelt congratulations to the Department of Chemistry and wish the FDP great success. Thank you all.
Thank you so much, ma'am. It's my honor to introduce today our esteemed research speaker, Dr. Srinivasan Hariharan. He is a researcher at the Institute of Theoretical Physics, University of Amsterdam, QSoft, a research center focused on quantum software. His work lies at the intersection of computational chemistry and emerging quantum technologies, with a particular focus on heterogeneous catalysis and surface chemistry. Srinivasan has experience running chemistry simulations on both high-performance classical computers and near-term quantum devices. He has published many papers in international journals, given talks at international conferences, mentored students across different levels, and taught a course on near-term quantum computing in the Masters in Quantum Computing Science program at the University of Amsterdam. We are truly privileged to have you with us today, sir, to share your knowledge and insights. Dear participants, kindly keep your microphone on mute and video off so that we can listen to the session without any disturbances. Now, I hand over the session to our distinguished speaker, Dr. Srinivasan Hariharan.
Yeah, am I audible?
Yes, sir. You are audible, sir.
Yeah.
Now.
Yeah, thank you. Thank you very much for the invitation. And thank you. I would like to first of all thank the organizers for this opportunity to deliver a lecture in the Faculty Development Program at the New Prince Sri Bhavani College of Engineering and Technology. Today, I'll be talking about quantum computing for quantum chemistry, or in general chemistry simulations. So since it's so I would like to give an introductory overview of what is happening in this field and why quantum computing is useful for chemistry simulations. Before I begin, I would like to thank my supervisors. I have three supervisors, one from physics, one from chemistry, and one from the industry, because my project is funded by Toyota Motors Europe. So Professor Karl-Jan Schoutens is my physics mentor, and Professor Lucas Fischer is my chemistry professor, and Dr. Sachin Kinge is the manager from the industry. And I would like to thank the funding agencies, Toyota Motors Europe and Quantum Delta NL, for the funding, and all the organizations for the organizational facilities. I work across three different institutes. And I would also like to thank the computational facility from the National Supercomputing Center called SURF, and also IBM Quantum for the access to their quantum computers. And I'm also a part of the quantum applications lab called QAL, who facilitated my projects, and also the Netherlands eScience Center for helping us build a package, which I will be talking about in the later part of the slides. I'm housed in the Algorithms and Complexity Group at the Center for Mathematics and Computer Science in Amsterdam, and also Professor Lucas Fischer's Theoretical Chemistry Group at the other university, the Vrije Universiteit in Amsterdam. So today I'll be providing an overview I'll start with chemistry, the state of the art or status quo, and I'll talk chemistry and how what are the limitations of some of the widely used methods, and where there is a need for quantum computing, because quantum computing is not a generally useful technology. It's useful for certain specific problems, which can be very useful. So, and then I'll briefly introduce quantum computing, and then a few quantum algorithms, maybe two, and then I'll dive into one, and then give you an overview of what is a quantum hardware and how can we run calculations on a quantum computer, and summarize with an outlook. So we all, since we are all chemists, we know that chemistry is not a computational science to begin with. So traditionally, chemistry is all about experiments and observations, and it has a very rich history spanning multiple centuries. And most of the chemistry happens in the wet lab, and most of our understanding of chemistry also comes from wet lab. So which means we do perform experiments in the laboratory and record observations, and we gain understanding. But there are also qualitative models that have been around for a few years based on our experience in the laboratory, which we also studied in our curriculum, like the Lewis structures, the VSEPR theory, and valence path theory, and etc. But to be very sure and to make my statement more concrete, the lab work and industrial scaling are very essential for having any practical impact with chemistry. But recently, I would say, I'm calling it recently, but computers have helped us in better understanding of chemistry. So Schrodinger introduced the Schrodinger equations sometime in 1925, and this is 100 years ago, and that is why we are celebrating the year of quantum by the United Nations. And since 1927, when the Heitler-London model for the hydrogen molecule was published, the computational chemistry has slowly started. But actual computational chemistry started with the introduction of chemistry software packages in the late 60s or early 70s. I think the first one was Gaussian. So only after 1970s, computational chemistry gained speed, and only after early 2000s, when we had all these advances in many different areas, we were able to perform very high quality calculations of relatively large systems. The computations have always complemented the traditional chemistry reactions by visualizing the molecules, the orbitals, and generating spectra for unknown molecules. So computational insights were often used to guide experiments. So to summarize, computations have aided in an understanding and accelerating discoveries. And because of this reason, computational chemistry is considered to be a third paradigm in modern science, along with experiments and theory. And the reason for this widespread use of computations is the improvements in the computer hardware. So now we have exascale computing in classical computing, where we can perform very, very fast computer simulations. And also, there has been lots of effort put into developing quantum chemistry algorithms for computational chemistry. And also, we have many different. We don't have to write the codes from scratch, but we were able to buy the package or download the package, and we are able to run calculations. And this has been very important in drug discovery, catalysis, material design, to name a few. So the idea here is predict before you make. That's how we work we also call it in silico experiments, or we can also call it predict before you make chemistry. So that's the usefulness of computational chemistry. And since we have the computational, we are able to perform computations, we need different methods. We have methods at different levels of sophistications. So wave function based methods, we call it Hartree-Fock method, post-Hartree-Fock methods like MP2, the molar perturbation theory, and CI, configuration interaction, CC, coupled cluster. We have different versions of it, coupled cluster singles, doubles, and perturbative triples is considered to be the gold standard in computational chemistry. And then on the other hand, we have density-based quantum mechanics, where we have density functional theory, which is the workhorse in many different fields, from organic, inorganic to materials chemistry, also including catalysis. And for systems that are relatively large, we also rely on semi-empirical methods like DFTB, density functional tight binding, and PM7 kind of methods. And if we want to run molecular dynamics, then we use interatomic potentials, which are now recently accelerated with machine learning for large systems. Each method is chosen based on the availability of the computational resources and the accuracy that is required. So there is always a trade-off between the accuracy and cost. So to put it into perspective, so here in this picture, there are x-axis gives us the cost of the calculation, and the y-axis gives the accuracy. As you can see, as we go from coarse-grained calculations and molecular mechanics, semi-empirical methods, DFT, and then correlated methods like CI and CCSTT, the accuracy increases, and so is the cost of the calculation. So when we need more accurate calculations, then we also have to spend more on getting those accurate numbers. So that's how usually computational chemistry works. So we have in one end we have Hartree-Fock, which is but on the other end we have full configuration interaction. So in the Hartree-Fock, what happens is that we let the electrons fill in the molecular orbitals up to the valence band maximum, which is, we call it HOMO, and then the Hartree-Fock theory is designed in such a way that when the electron feels the field of the remaining sea of electrons. So that's why it's called mean field. And the big problem with Hartree-Fock theory is that it ignores correlation. So that's the main drawback. But Hartree-Fock remains the basis for many post-Hartree-Fock methods, as the name suggests. So as you can see, yeah. This part of the picture corresponds to Hartree-Fock. So these lines are called molecular orbitals, and these dots correspond to the filling of electrons. So that's what, as simple as that. So we express the Hartree-Fock as the Slater determinants, where the electrons occupy certain spatial orbitals or spin orbitals. And then on the other end, we have a full configuration interaction. Given within the given basis set, it's exact because it takes into consideration all possible configurations, as shown in the right hand side, the linear combination. So basically, it takes the Hartree-Fock and excites one electron to the higher level or more electrons to the higher level, and it takes all possible combination with a coefficient. So that is why it is called linear combination, and that is also why it is called full configuration interaction. So but actual computational chemistry does not have end with Hartree-Fock, or even for water molecule with a reasonable basis, we cannot run a full configuration interaction in today's available computer. So we have to find a compromise. That is why we have computational chemists have developed many methods like MP2, CC, couple cluster, CAS-CI, and CAS-SCF, etc. So here the problem is that with increasing accuracy, as I showed in the previous slide, we hit a computational wall. So the summary of this part of my talk is that there is no universal solution. There are trade-offs. Some methods work well for some problems, but it fails for others. And there is always a question between accuracy and efficiency. So we chemists still choose method case by case. So if it is an organic chemist, they have their own favorite functional. If it is an inorganic chemist, they have their own functional. And if somebody is working on catalysis kind of problem, they also have their own favorite functional that works for them. So there are some limitations for the widely used methods like density functional theory and couple cluster. Within density functional theory, we have over 600 functionals. And there was also a question of which functional to choose for a given problem. And also, I will get back to this little later. There is also a problem with static correlation. And also, the couple cluster theory is also considered to be the gold standard. Also, faces problem when it comes to multi-reference or also the static correlation problem. So whenever we use single determinant, a Slater determinant to express the occupation of electrons in orbitals, for certain problems we fail. So like bond dissociation. So water molecule in its molecular state, it does not have static correlation. But when we dissociate one of the OH bond, that's where static correlation kicks in, and many methods fail. And also, when we study inorganic metal complexes, also static correlation is a big problem because we need to consider the changing spin states during the reactions. So what is the static correlation? So static correlation is easy. The definition of static correlation is easy because that's the difference between the Hartree-Fock energy and the exact full CI energy. So that's rigorously defined. I mean, but this correlation energy has been divided into two. So the dynamic correlation and the static correlation, which is not very well defined. So dynamic correlation is relatively simple, which can be modeled using perturbation theory, and also most of the DFT calculation captures the dynamic correlation. So dynamic correlation comes into picture when we take all possible orbitals, within the given basis. And there's another correlation which is called static correlation, when, like I said, when you have to take a linear combination of multiple configuration, this appears. And one of the classic examples is hydrogen dissociation. When hydrogen dissociates, so there's always a question between whether it's ionic or covalent. And also, most of the methods cannot describe hydrogen dissociation or nitrogen molecule dissociation. So, getting static correlation right is important in certain cases. So some of the, apart from hydrogen and water, let's look at some realistic examples. Here, I am showing an example of oxygen molecule dissociating on an aluminum surface. So here, the x-axis shows the distance between oxygen and oxygen. Y-axis shows the difference between the oxygen and aluminum. So oxygen comes in, and then it hits the surface, the aluminum surface here, and then it dissociates. So what happens is that the density functional theory with many of the functionals, here there is white in color. White means negative. So what it says is that the potential energy curve calculated using many density functionals shows that there's no barrier for this reaction. So all the molecules that comes in dissociates. But unfortunately, that's not true. So when we use a accurate wave function based method embedded in density functional theory, we see that there is a barrier for this reaction. So that's why we need more accurate methods. Density functional theory is not sufficient for certain chemically relevant places. So, and then another example from homogeneous catalysis. Here you can see that this is a complex. Here oxygen is bonded to 3 metals. So you have iron and metal 1 and metal 2. So these are the cases where strong correlation is important. So this concerns a reaction where ethane is converted into ethanol. And this is the most famous example in the quantum computing context, because this is the structure of nitrogenase enzyme, and this is the iron molybdenum cofactor, which which naturally converts nitrogen to ammonia. The nitrogenase enzyme present in the roots of certain plants can fix nitrogen to the plants, which means that it can convert nitrogen to ammonia. But the industrial process that exists today operates at very high pressure and temperature, which is the famous Haber-Bosch process. But this can convert nitrogen to ammonia very efficiently. So people are looking at modeling this cofactor and trying to come up with a more efficient catalyst for ammonia, converting nitrogen to ammonia, because that's one of the reactions that's very important for the humankind. And that is something we need to make it more efficient. Since we are not able to run the calculation for full CI for many reasonably big systems. Here for hydrogen, we can run with reasonably big basis sets. And when we go to water, we have 10 power 9 configurations in a double zeta basis set. And for benzene, we have 10 power 46 configurations. So, which means that we don't have enough atoms in the universe to store the information that is required to perform this calculation. So this is when we take all possible excitations of the electrons in the molecular orbital to the virtual orbitals. But there is a shortcut, which is people call it the active space approach, where the low energy, fully occupied orbitals are not touched. We call it the inactive space, and very high energy orbitals, which are empty, are also untouched. That's we call the virtual space. And there is a middle region where we operate, which is full CI, full configuration interaction within this middle region, which we call the active space. So we can systematically increase the active space and perform our calculation. So this is called the active space approach. We call it CAS, complete active space. Like I said, it is taking into consideration all possible configuration within this active space. But the determination of this active space for a given problem depends upon the problem. So it's more of an art than science. People are trying, there's an entire research area focused on coming up with automated ways of constructing these active space. So whenever you see in a paper that says cast MN, or the first M corresponds to the number of electrons and N corresponds to the number of orbitals. So if we do M choose N, we put the permutations, then we get that number of configurations within the active space. And one of the very important things is that the orbitals representative of the problem should be present in the active space. And this is one of the widely used methods. And in CAS-SCF kind of CAS approaches, the CAS-SCF, which means self-consistent field, complete active space self-consistent field is the most successful. And people have done calculations for up to 20 electrons and 20 orbitals in high performance computers. And with lots of approximations, people have also done calculations with 44 electrons and 44 orbitals. And also using another method called density matrix renormalization group, people have done calculations up to 84 electrons and 84 orbitals. But this is all approximate, right? With lots of approximations. So the problem here in performing multi-reference calculations is lots of computational resources, and it is heavily dependent upon users. The idea here is that what is the problem with the computational resources? Because it's practically impossible to store all the wave functions on classical resources, even if it is a high performance computer. Like I said, we have to store all of these configurations. And there, quantum computing can help because in principle, quantum computing has large enough memory to manipulate configurations in superpositions. So this is the promise of quantum computing that we have. That is why quantum computing is interesting for chemistry. And naturally, there is a connection between quantum chemistry and quantum computing. So here, if we take a typical spectroscopic experiment, then we see that when we shine a light on a molecule, we call it there are three stages. One is the preparation stage where we prepare a molecule, and there is an evolution stage where when we shine a light, depending upon the spectroscopy, and then it evolves over time, and then we do perform a measurement at some point. So that's what we show here. It is carbon dioxide molecules and its three normal modes, and we finally get a measurement, and we can measure the spectra. This wave function, which could be a representative of the given molecule. And here is the time evolution operator, which operates on this wave function. And then we finally measure an observable. And also in quantum computation, it is very similar. We prepare the qubits in certain states. Here, it's all zero state. And then we apply these unitaries, which are these kind of operators. And then we finally make measurement. So that's because I mentioned qubit, I have to explain what a qubit is. A qubit is nothing but a quantum bit. And here you see that this is called a Bloch sphere. And this, with using this Bloch sphere, you can explain what a qubit is. So here on the two poles, we have the zero state and the one state, the two states. And sorry. And then the point on the globe in any of these points corresponds to a qubit state, which can be described by two angles, theta and phi. There are two types of errors that's possible. One is the bit flip. What happens is that when we want to flip the state from zero state to one state, it does not do it perfectly because of the environmental noise. So that's called the bit flip error. And there is also a phase flip error, which corresponds to the point along this direction. So these are the two major kinds of error that's possible in a qubit or in any quantum computer. So how do we manipulate the qubits? To perform a useful calculation, we have to manipulate the qubits. So for that, we use quantum gates and we build quantum circuits. So for example, here we have two qubits, qubit 0 and qubit 1. This corresponds to qubit 0 and this corresponds to qubit 1. Here, the gate X flips the state from the qubit 1 is in 0 state. And here, since the operator, this state is flipped from 0 to 1. Similarly, there are also two qubit gates. These two qubit gates are used to perform entanglement. And then we have additional rotation gates. We can rotate along the axis. And finally, we can add a measurement because until here, we cannot read the state, what we are preparing. But when we add the measurement, we can definitely know what state we are working with. And because it's quantum computations, we get probabilities. So for example, if we perform 1024 measurements, we get almost equal probability of these two states, state 1, 1 and state 1, 0 in this case. So this is how we perform computation, but the actual quantum circuits that's used are long and huge. We need to construct those quantum circuits to perform any useful quantum chemistry calculations. And because quantum computing has gained attention in the recent years, usually this field is divided into two eras. One is the NISQ era, noisy intermediate scale quantum era that we are living currently, and other one is FTQC, which is fault tolerant quantum computing. So in the NISQ era, we operate with a moderate number of noisy qubits in the order of 100 to, I think today we have 150 qubits superconducting. And then here we use near-term quantum algorithms that's not fully quantum. We have classical quantum loops, and then there's a need for error management. So we use some techniques to suppress some of the errors and mitigate some of the errors. But when we move to fault-tolerant quantum computers, we have error-corrected qubits, which means all the qubits are working without errors, and full error correction is possible. So for these two eras, there are two different algorithms. One is the variational quantum eigensolver, and the other one is the quantum phase estimation. Quantum phase estimation is more suitable for fault-tolerant quantum computer, and variational quantum eigensolver is more suitable for near-term. So the idea of both of these algorithms is to calculate the total energy of the system. Whereas one is suitable for the noisy machine, and the other one is suitable for fully error-corrected quantum computer. So today, I'll only talk about variational quantum eigensolver and not about the quantum phase estimation. So how do we perform a calculation on a quantum computer using variational quantum eigensolver? First, we choose a system, and then we generate the Hamiltonian of the problem using any classical computational chemistry software. And then, because these are electrons or fermions, we have to map from the fermion to qubit. There are multiple ways to map this. And then we prepare the Hartree-Fock state on a quantum computer. We need a wave function guess for a given system. That's what we call an ansatz, and that is also expressed in terms of parametrist quantum circuit. So this together, the reference state and the parametrist quantum circuit is called the trial state. And then we need this Hamiltonian prepared using the fermion qubit mapping to calculate the expectation value. And if the expectation value, it checks with the expectation value of the previous step, it variationally lowers the energy until the energy converges. So here the ones shown in purple are performed on a quantum computer. The one shown on the red is performed on a classical computer. So it is a hybrid classical quantum algorithm. And what we try to do is variationally go to the ground state energy, but we cannot achieve the true ground state. Settle down for an upper bound of the true ground state energy. And there are multiple applications that has been proposed for these kind of calculations, and starting from molecular structure prediction to using in drug discovery, and ground state calculations, photochemistry, complex dynamics, and cheminformatics. But in our group, we focus on these three parts where we use quantum computing for ground state chemistry and photochemistry and complex dynamics. And we are a group, we call ourselves Quantum Computing for Quantum Chemistry, or QC Square Group, which is a collaboration between three different universities. One is the University of Amsterdam, where I work, and the other one is the Vrije Universiteit or Amsterdam, where I also work partly, and then the Leiden University. So this is a collaboration between the three groups, and we have a few researchers working on many of these topics that's related to computational chemistry. So I'm working primarily on photocatalysis and heterogeneous catalysis, and I'll give one example of what we have done using quantum computers. So in any general photochemical mechanisms, we need an excited state. A reactant is pumped to the excited state, and it crosses a transition state and comes down to products. And there are many mechanisms with which it can come down to products. but one of the more prominent mechanisms is the non-radiative transition, so which is called the through conical intersection, because this looks like a cone, and getting this right using density functional theory is impossible. So this is a suitable problem for quantum computers. So, and also this, since it concerns two different electronic states, we need to democratically, equivalently describe these two electronic states. For that, our group in Amsterdam developed an algorithm called state averaged orbital optimized variational quantum eigensolver. Variational quantum eigensolver was what I described 2 slides ago. And that is the quantum counterpart of CAS-SCF, which I described a few slides ago. That is also the state average part, which means that we are able to calculate both the states democratically. And it can be this calculation can be run on quantum emulators or on quantum hardware. And it has 2 loops. One is the VQE loop, the variational quantum eigensolver part, and the other one is the orbital optimizer part. Together, this algorithm get the lowest possible energy. The reason why we need orbital optimization is that if we calculate conical intersection, for example, for maldiimine molecule, which is very small, with only CAS-SCI, which doesn't have any orbital optimization, we don't see the conical intersection. But when we do the orbital optimization, we encounter the conical intersection. That is the reason why we need to do the orbital optimization here when we consider 2 different electronic states. For my case, we have studied the photodissociation of water and titanium dioxide. Sorry for the typo here. And here, what the experimentalists have shown that water does not react on this non-stoichiometric titanium dioxide Ti2O4, titanium dioxide dimer. But when there is one additional oxygen atom, which is Ti2O5, water reacts to form hydrogen peroxide. So to support their calculations, they have their observations. They did these calculations where they used 3 different methods: one for the ground state, one for the excited state, and one for the conical intersection. So, but which is not very consistent. So we chose this reaction to see if we can calculate this conical intersection using quantum computers. And yes, we were able to. The SA CAS-SCF is what the circles and squares, empty circles and squares, and filled circles and squares are calculated using quantum algorithm. And we are able to calculate the conical intersection. And we are also able to attribute the conical intersection to the oxygen bond. This is the additional oxygen. This is Ti2O5. So the additional oxygen is responsible for the dissociation of water. So this is what we found. Yeah, this is one of the examples that we worked on. And most of these calculations that I've shown so far were run on simulators, which is the high performance computers or laptops where we can emulate a quantum hardware, because quantum calculations are mostly matrix multiplications. If we can perform these matrix multiplications very well on a classical computers, then we can do that. But there is a limit. We can only perform up to 34 qubits to any quantum calculations on a classical hardware. So we need quantum computers. And some might have seen this picture. So this is the IBM's superconducting qubit. So these are gold fittings. So what happens is that since it is a superconducting qubits, at this part of the quantum computer is very cold. It is almost close to 0 Kelvin. Like realistically, it is 0.015 Kelvin. And this is called the dilution refrigerator because this part of the refrigerator is hot, and room temperature, and it cools down as it goes down. So to perform error-free calculation, we need to, for the superconducting qubits, we have to cool it down to very low temperatures. But there is no one technology with which we can build quantum computers. So we have multiple technologies. Out of this, the front runners are superconducting qubits, trapped ions, and neutral atoms. Superconducting qubits are pursued by IBM, Google, big companies like IBM and Google. Trapped ions like Honeywell Quantum is doing trapped ions. Neutral atoms is done by a few companies in the US like QEra. I think topological qubits, Microsoft is working on topological qubits, and they're also heavily investing on other technologies as well. So today, there are multiple technologies to build qubits, but it is not very clear which of these technology will be a winner in 10 or 15 years time. So there is a very intense competition between many of these technologies in making their technology successful. So the biggest problem in today's quantum computers is noise. So like I said, there are two possible errors. One is the bit flip error. You might not get the right state when you flip the state of the qubit. And also you might not end up in the right place when you rotate along this axis. So these are the two possible errors. There are a few methods to mitigate. I mentioned these terminologies before. I'll try to explain this. There are three main error suppression technologies in general. We call it error mitigation, error suppression, and error correction. So in the NISQ era, the noisy intermediate scale quantum that we are in today, we perform mostly error mitigation and suppression. But as we go towards fault tolerant quantum computing, we should use both error suppression and error correction. So error correction today, there's lots of places putting lots of effort in coming up with very good error correction algorithms. So the idea here is with error mitigation, we try to reduce the impact of the error with zeros and ones. So after measurements, we try to reduce the impact of errors. And with error suppression, we do it on the fly. We try to reduce the sources of errors. Error correction is that we use multiple qubits, physical qubits, to correct the error on one qubit. So these all together, for example, 10 to 15 qubits work together to correct the error on one qubit. So that one qubit we call a logical qubit, but which requires many physical qubits. So that means there's a guarantee that the computation is almost all the time it's correct. So that's the difference between these three terminologies, but all these three terminologies and methods are useful in different stages of building quantum computers. And we had a special access to the IBM quantum computers through the Quantum Applications Lab. And this is how the qubits are arranged. Here, the dots are the qubits and the lines between them are the connections. And as you can see, they are in different colors, and all qubits are equal. Some qubits are coherent, some qubits are less coherent. So when we run the calculation, our results of the calculation depends upon the coherence of all these qubits and also the connections between them. So that is very important. So, and as they calibrate once or twice every day, the qubits coherence time changes a little bit. So we might not get the same results for calculations done on two different times in a day or in consecutive days. So we did a calculation for a hydrogen molecule with a Cas2 with 2 electrons in 2 orbitals. And when we did this calculation on a simulator using VQE, we were able to achieve the results, the right results, the reference energy. But when we did the calculation on an actual quantum computer, due to errors, we were not able to achieve this. It's orange lines. So this, we call it no error mitigation. And these three methods are error mitigation methods. The one is called dynamic decoupling. Other one is zero noise extrapolation with two different number of shots. So when we increase the number of shots, we get more probable outcome. So the increasing in number of shots also increases the time of the calculation. So that means we also pay more. So these set of calculations are very small, but we use this calculation to benchmark how much we would pay for calculations with and without error mitigation. So in case if some of you are interested, so this is called the QC Square software, which we built at Amsterdam, and you can download at the GitHub and you can try. So here we tried to interface agree both to the quantum chemistry software and the quantum computers on the right side. So we built a middleware kind of software. So you can take the Hamiltonian from and the reference states from one of these packages and process it within QC square, and then you should be able to run on the simulator or an actual quantum computer. So this is what it does. And recently, we also published a perspective paper in the Journal of Chemical Information and Modeling on how can we use quantum computers to model heterogeneous catalysis. And we also developed an algorithm for physics kind of problems. How do we place the different qubits on the virtual qubits that we have in the algorithm on the actual qubits more efficiently? And as I said, as the co-organizer said, that I also taught a near-term quantum computing course in the new Masters in Quantum Computer Science at the University of Amsterdam last year. So yeah, I have that experience as well. Going forward, what we are trying to achieve is that even we have noisy qubits, we are trying to as I said, there are two types of different eras. One is the NISQ era, and the other one is the fault-tolerant quantum computing era. But I think both alone will not be very useful for chemistry. We are trying to achieve a sweet spot where we can be resource efficient, because the right hand side is more resource intensive and the left hand side is more noisy. So we need to come to a compromise and achieve a sweet spot to perform reliable chemistry calculations, which is both resource efficient as well as chemically insightful. Yeah, it's always, most of the quantum computing talks will have a quote from Richard Feynman, who was one of the founding fathers of this field. But I would like, because there's lots of hype going around in quantum computing today, I would like to end with the quote which says that for a successful technology, reality must take precedent over public relations, or nature cannot be fooled. So there is hype because they need to generate funding, but we should also be very realistic in what we can achieve with these existing quantum computers. I would like to thank you all for your time, and I'm happy to take questions.
Thank you so much, sir. That was indeed a highly insightful and enriching session by our distinguished speaker, Dr. Srinivasan Hariharan, on quantum computing for quantum chemistry and overview. The session has given us a fresh outlook on the possibilities of quantum computing in the field of chemistry. The floor is now open for queries. I request participants kindly unmute themselves one by one and can ask questions to the speaker.
I have one question on the chat, which asks how, when simulating reaction mechanisms, how do quantum computers compare to classical high-level methods? So the problems that can be solved with coupled cluster theory do not require quantum computers, because like I said, coupled cluster is a single reference theory, so we don't need a quantum computer. So there are other systems where coupled cluster theory fails. There are many systems these days, because like when we have biradicals, when we have different spin states, coupled cluster theory fails. So those are the cases where quantum computing can be useful.
இதுக்கு அடுத்தவன் பாருங்களேன்.
Participants, kindly, those who have queries, just unmute yourself and ask any questions regarding the topic. Others, please kindly mute your audio.
Hello, sir. Hello, sir.
Yeah,
ID தான் வரணும், பேர் வைக்கல. நான் mute போட்டேன் சார். இந்த mute போட்டேன்.
Sir, Srinivasan sir?
Yeah, I can hear you.
Okay. Okay, it seems there are no further questions from the
Hello, sir.
participants. Okay.
This-
Okay, go ahead, ma'am.
Hello, sir.
Yeah,
Hello, sir.
I can hear you. Please go ahead.
Sir, thank you for your nice presentation, sir. I have a few doubts. I'm
Yeah.
working on polymer metal oxide composite, sir.
Yeah.
For that polymer metal oxide composite, can we predict the functional group with the quantum chemistry? Is it possible or not?
Yeah,
Like FTI.
it is possible, but for realistic molecules, quantum computing is not ready yet. It takes at least 5 years. Even you can try with traditional quantum computational chemistry softwares. That should be able to do the work for you at the moment. So within quantum computing, it's not ready yet. It takes at least another 5 years to do something very useful.
Okay, sir. Thank you, sir.
Participants, if anybody having any queries, kindly unmute and can ask questions. So it seems there is no further questions from the participants. With that, we conclude the question answer session. It's my privilege to invite our professor, Dr. Ida Ma'am, to deliver the vote of thanks.
Good afternoon, everyone. It's my privilege to propose the vote of thanks for today's session. At the outset, I extend our sincere gratitude to Dr. Srinivasan Hariharan for his thought-provoking and enlightening lecture on quantum computing for quantum chemistry and overview. The way you unfolded the fundamentals of quantum computing and connected them with practical applications in chemistry has truly expanded our horizons. Your session has not only enriched our knowledge, but also motivated us to explore the vast potential of this interdisciplinary domain. I would also like to express my heartfelt thanks to our management, our respected principal, heads of the departments, and faculty members for their constant encouragement in organizing this online faculty development program. My sincere appreciation goes to our head of the department of Science and Humanities, Dr. S. Shivahami, and organizing team of chemistry department for their meticulous efforts and smooth coordination. Last but not least, I thank all the participants for your keen interest and active involvement, which added great value to this FDP. Once again, I thank you, Dr. Srinivasan sir, for sharing your expertise and making this session memorable. Thank you.
Thank you so much, ma'am. Feedback link is now posted in the chat box. We request you all to fill it out and submit. So finally, we are leaving with an enriched understanding and a new vision of how quantum computing is shaping the future of quantum chemistry. With that note, we officially conclude day 1 of the 5-day international online FTP on recent trends in chemical sciences and engineering. We look forward to you all tomorrow for the day 2 of the FTP. Kindly join at the same time. Thank you all.
Thank you.
Thank you, sir. Thank you so much.
Srinivasan sir, thank you so much, sir, for your valuable time for us. Thank you so much. And
Thank you.
dear
Thank you for the
participants, thank you
opportunity.
all for attending the wonderful FDP. Thank you so much.
Thank you.